Okay, so we were looking at this issue of traction vectors, and traction vectors or traction vector which will be denoted by, let's say, T bar. It's also called the stress intensity or stress vector, but basically this idea of traction vector is rather simplistic. If you have a body on which forces are acting, then if you happen to take an arbitrary cross section somewhere here on the body, so this is an arbitrary small area, right? So this is dA. So on this arbitrary area you will have some force acting, right, in some direction or the other. So there will be some force, right? So if you define a quantity such that this traction vector is basically this force, the amount of force that is acting on this area dA, and then you take the limit of this quantity. Okay, so sorry, I should have left some space for that. So limit as delta A tends to 0 or dA tends to 0, sorry, I've written dA, so I'll just use that. So dA tends to 0, and we are looking at this force which acts on this surface, right? So I have a small surface area here and I am trying to figure out how much is the force. Now here I am defining a new type of vector which now has the units of force per unit area. Okay, so this has the units of force per unit area, and when we were trying to do this, then we realized that if you make an infinitesimal cube, then you will have traction vectors on phase 1, phase 2 and phase 3, right? So this was where we had said that this is basically direction 1, direction 2 and direction 3. So the way the directions have been taken is that the right hand rule is satisfied, right? Now on this particular phase which is pointing along 1, you have some net traction vector, and this traction vector is now going to be given by this quantity sigma 1 to E2 hat, and okay, I'm running out of space here, so I'm just going to squeeze it in, right? And similarly for the other ones, I'm not going to write all of them. So you have similar equations, and these are all vectors, right? So T1 here, this denotes this particular phase, the entire force acting on here, and these quantities which are coefficients of this unit vectors, this now become what I call the stress. So this is now your sigma 1 1, and we have already done this. I'm just doing a quick recap of last class. So sigma 1 2, this is sigma 1 3. Let me use a different color, just a second, sorry, because we'll have so many of this that it might be difficult to remember or find. So this is now going to be sigma 2 2, sigma 2 1, and this is going to be sigma 2 3. Okay, and this is sigma 3 2, this is sigma 3 1, and this is sigma 3 3. Now all these different, this is a pictorial representation of this equation. I had already told you that. So basically all these traction vectors are surface forces. So surface forces acting on this infinitesimally small control volume, right? And we are obviously going to look at a situation where this entire control volume is going down to 0. Okay, so if this is the dx length, then we are looking at the dx going off to 0 limit. So then this will form this quantity sigma ij here. This sigma ij is going to be my stress component. And you can see that how you will have 9 components here, right? So although you have 3 vectors, but because you are relating it to the 3 unit vectors, you now have 9 components in all, right? So this quantity is now going to be called stress, and another way to look at this is that so another way to look at this is that the the traction vector is basically given by this stress tensor transpose of that with n hat. So if you have an arbitrary area with its normal being n hat, then we'll see this result. I have not shown it here, but I am calling into here an equation. This is also called the Cauchy's formula, and we'll see that in a second. I've already drawn that for you separately, but we'll come to that. But this relates so basically this is how it relates to force vectors, and this is your linear transformation going from one vector, which is a surface direction vector, and it gives us the traction vector, right? Okay. So this is how we'll get it, and then of course if you have to get the force, you just multiply it with the area, right? So if it's an infinitesimal thing, then you just do a dA, and if it's varying over area, then you just do an integral, and then you find the total net force, right? And the way we looked at all the rules for doing this, we said that on the positive faces, these quantities face in the positive direction, okay? But on the negative face, this sigma 1 faces the negative direction. So that's how when you do this, so if on the other face, since E1 here you are looking at the normal to this face is in the other direction, that is why the sigma 1 has to be in the other direction to nullify for that. Okay, so what will happen is all these different components will reverse on the other face. Okay, so this will become sigma 1,3. On this face you will have sigma 3,3. This will be sigma 3,2. This will be sigma 3,1. And here you will have sigma 2,3. You will have sigma 2,2. And you will have sigma 2,1 here. Okay, fantastic. We still have to see how this formula came into being. For that, okay, before I go to that, just a second, I'll write a couple of more important points. Okay, so just make a couple of important notes, and then we'll go look at that. So the notes are that my sigma ii, if I write no sum, these are my normal stresses. Okay, and sigma ij, I not being equal to j, these are referred to as shear stresses. And you can have negative, so if sigma ii is negative, then element is in compression. If sigma ii is positive, okay, no sum, okay, sigma ii means sigma 1,1, and so it's not the sum of the sigma 1,1, sigma 2,2, not that, but I didn't have space, I mean I just forgot. So these are all again no sum. Okay, so these are no sum, although there's a repeated index. So if sigma ii is positive, then element is in tension. Okay. So with this, I hope we have getting some understanding of this quantity called stress. Now we want to prove this, and what we are wanting to show, and I've already done it for you, and this is just extra reading. So what I've done is, these are the different axes. So this is your, obviously again 1, this is your 2, and this is 3. So the numbering is exactly the same. And here we have drawn an arbitrary triangle. Okay, and this arbitrary triangle has a given normal vector n hat, and on this arbitrary area we have a traction vector that is acting, which is t bar, and the n subscript is just supposed to show that it is associated with the superscript is supposed to show that it is associated with this normal vector here. And what we have done is we have drawn the other components of the stress on the other faces. So this is an element that is being so there are this other face is there on the plane 2 1. There is this face which is on the triangular face on plane 2 3, and this is the second triangular part in plane 3 1, and combined with this tetrahedral element, you have a complete unit. Okay, so we are again looking at infinitesimally small element, but this time we have cut it such that you can just think of it as if we have taken a plane and cut it through one of the cubes and cut it through one of the vertices, and you have this triangular shape. So you now have an arbitrary shaped area which has a given normal vector, and let this area be dA n. Okay, so n is just to make sure, the superscript is just to make sure that we understand which area we are talking about, because there can be so many areas, and you know, this drawing is just two dimensional, so it's easy to confuse. So the question is, what are the areas of these other faces? Well, this is dA E1 hat, dA E2 hat, and so these are all the areas that are the triangles that are aligned with the axes. That those are basically nothing but the projections of this on that plane, right? So in order to find that, all you need to do is to take this area and dot product it with this vector to get the areas of these other triangles that are enclosing this volume. So when you do that, and then you apply Newton's law to the element in the x1 direction, then the Newton's law is rather straightforward. You have the mass and you have the volume. So this is the volume, by the way. So we have always done the V with a cut for that. So we'll do that again. So once you have that, then this is the summation F, and then so this has to be the summation of all the forces, and that can now be written as the traction vectors multiplied by the area. So you write down all the different forces that are acting. So this is the force that is acting on this randomly oriented face, and then you have the stresses that are acting on the other faces, but for that you have to now multiply it with the corresponding area to get the net force, right? And then this is the body force again. By the way, this is again the volume, so I have to do that. I should do that again here, right? Okay. So now that you, okay, so when you get this portion, then if you just rearrange all the terms, you can get this traction vector on this side, and you can rearrange the terms to look like this. Now when you take the limit of dAn going to 0, what will happen is this term, which is a volumetric term, it will actually go to 0, and you will only be left with the surface terms. This, by the way, is a very interesting phenomena, because here you are taking an infinitesimal volume, and what you are saying is there are all these surface forces, and then you are balancing with the body force here. This is the body force F1 and the acceleration. But as you shrink this, as you take the limit of dA tending to 0, this mass term of this control volume ends up becoming negligible, and it shrinks faster than the surface forces. And what happens is this particular term, it goes to 0, but the rest of the term remain. Okay, and thus you will have the traction vector. It can be written as sigma 1 1 n1 sigma 2 1 n2 plus sigma 3 1 n3. Basically, if you take an arbitrary cut through your cube that we are talking about, then if you want to know what is the traction vector that is acting there, all you need to do is to do this particular calculation, which is Ti. Okay, this is I, by the way, just in case there might be any confusion. Let me rewrite that. Okay. And it is related to this surface stresses and the normal components through this particular formula. Okay. So this you can see. So I hope you, so this is also known as the Cauchy's formula, and this particular stress, which is associated with these imaginary control volumes that are drawn, is also called the Cauchy stress. There are other types of stresses which are possible depending on how you define this n vector, and we are not going to go into that, but there are other ways of doing it. But here, this control volume that we are taking, this has nothing to do with the material point. Okay, so it's just an imaginary area that we have sought without ever referring to how the material is behaving. Okay, so this stress is also known as Cauchy stress. So I will give you this PDF as a separate document, and you can look at that. But basically here this stress tensor, now this becomes the Cauchy stress tensor, and this is the other form of writing the same equation. Okay. I've also asked you to check for yourself that the stress tensor is symmetric. I'm not going to do it right now, maybe somewhat later, but please check it out yourself. It's a very simple proof, but it's very enlightening if you do that. Okay, I am not going to do that because I want to move on to something else, which is the linear momentum conservation for a differential control volume. Okay, and now if I have to just go back, we've done this for just a second. I'm just searching for where we did the right. So we were looking at the differential approach, and then we were doing the conservation of mass for a differential control volume. And what we had done is we had taken this differential element, and we had, one of the ways was to just look at all this fluxes through the different phases, and then when you had equated all the fluxes, then you could have got the continuity equation, which is this one. But we had also looked at another way of doing the same thing, and here we had just taken the Reynolds transport theorem, and then we had gone from there. So we had looked at the integral approach and used that, and gotten the same relevant equation. So today what we'll do is just we'll look at method 2 again. So you can always do this form of approach, but we'll just take the second one. It's easier. Actually, it takes lesser time because we have a lot of ground to cover in the next few weeks. So we will take say the recall the integral form and if you want to recall the integral form, it should be there somewhere in my notes as well. Let me see if I can quickly find it. If I can't find it, I'll just write it down all over again. But yeah, so this is the equation that we had been working with, right? So you have the body forces and the surface forces on the control volume, and on this side you have the time derivative of the momentum inside the control volume, and then you have the flux through the control surface. Okay, so let us just go ahead and write that. So I'll just change the what is written on which side, and the reason I'm changing it is because, well, this is how they usually do it. So in F equal to ma, you write F on the left hand side, but in fluid mechanics we end up writing the other term on this side, and we tend to write the force on the right hand side. That's just what people end up doing. Okay, so you have this u bar here, and then you have rho u rel dot dA, and then you had the F body plus F surface. Okay, now what I'll do is I'll not deal with all the vector terms, is that this makes life very complicated. So I'll just drop this, and I'll only consider one of the components, and that can be just any ith component, right? So I can just put I here. Okay, so I have the integral form, and we are going to do exactly what we did for the control mass. Okay, so for first term, rather than for the first term, is we will consider a fixed control volume. Okay, so what happens to the first term? For the first term, you have the ddt of this ui rho dv, right, over the control volume, and this quantity will now become, I can take this this time derivative inside, and now just put ui rho dv, right, and my u relative will be simply u, right, for a fixed control volume. Now my body forces fbi, right, this is the net body force on my entire control volume. So I can just write cv, and this is the volumetric term multiplied by rho dv, right. Similarly, for the surface force, I can now write it as the integral of the entire surface forces, which is given by what? It's given by my traction vectors, right? That's my, this is, remember, this is the force per unit area, and if I have to find the net force, then I need to multiply it with the area and then do an integral. So if I need to do that, all I need to do is to consider this quantity. So for my control volume, this quantity becomes, sigma ji nj into dA. This hopefully is giving you some idea of where we are headed. Now we have two type of terms. We have a control surface and we have a control volume, and these terms are not here you have a control surface and a control volume. On this side also you have a control volume term and a integral over the surface term, and we need to make them compatible, and we just need to convert all the control integral over the control surfaces into integral over the control volume. So we need to convert all the double integrals into a triple integral. How do we do that? By utilizing Gauss's theorem, right? So by using Gauss's theorem, just like we did it for the last time, my first term is my ui rho u bar dot dA, right? So this will now become my integral over the control volume, my del dot this term ui rho u bar, and now this is now going to be, this is no longer going to be dA, this is just going to be dV. Okay, so that helps simplify my first term, and this can also be written as, if you want to simplify your life, okay, maybe I'll just write it here itself. I'll just make it small. This is equal to integral over the control volume del. So my I is already taken, but I have a dot product here with another vector. So I'll just choose another repeating index, and then it may call it j. So this will be rho, this will be ui, and the repeating vector index will be uj. Okay, good. Okay, so we have simplified one of the terms. Now let's do the same thing for the other one, which is on my right hand side, which was sigma ji nj dA over my control volume. So if we want to convert this, sorry, this is control surface. So if you want to convert it to this term, then you have to take the derivative again, and I'm just going to write the expression. This is what it will come out to. Okay. So substitute all this. So you now have a control volume term, and then the first term is this quantity right here, right? So I have del t ui rho, right? That was the first term, and then my second term is this. So you have my del xj rho uj ui, okay, and then you have the force terms, which for this case is just rho times f minus rho times f b comma I, and then you have the last other term, which is this one right here. So if I put that here, you have sigma ji by sigma xj. Okay, and this is dV. Fantastic. So now, since this choice of control volume is arbitrary, this entire integral here has to be equal to 0, right? So this implies that my del t of ui rho plus del xj of rho ui uj minus rho fb comma I minus del sigma ji by del xj equal to 0. Okay, this now is my important equation. And this is important because it has this particular term. Now look at it, this equation. These are the velocities that you are after. Okay, rho is a material property. This you must know a priori in order to solve the problem. But now you have this divergence of stress term. Now what are we going to do with this? You cannot solve this equation because this term is not known. It is not known in terms of these unknowns. You want to be solving for ui. That's what you are wanting to do. But I now need a relationship which will relate my stress to my strain in the system or the strain rate, and then I can replace this term and have maybe an equation in all u or something like that. We'll see what it comes out to, but that's what we want to do. So that's where the constitutive law comes in. We need to get rid of this term and replace it with something else such that it renders this equation solvable. And that's why in the last class when we were discussing constitutive laws, that's where this will come into. So we next point which we'll go into is called the constitutive law. Okay, so the constitutive rule. Now in order to find the constitutive rule, you need to go into a bazaar, and you will get into a bazaar of fluids, right? And when you go there, you are going to be asking for fluids. And when you ask for fluid in the bazaar, you have a lot of shops. They're all selling fluids, and you are going to ask them for different type of fluids, and you want, with each fluid, you want the shopkeeper to give you the constitutive rule. Okay, but when you go to the bazaar, what kind of fluid are you going to find most? So it turns out that one of the most commonly encountered fluids in our bazaar is water. There is more of it than even the land masses that are there. So this is, by the way, the globe. I hope it's a shoddy drawing, but this is the earth, this is the Indian peninsula, and this is water. And there is one more type of fluid that seems rather common, okay, and that is okay, that was not a good drawing at all. Let me try one more time. Okay, so okay, it's gotten something. And then you have the atmosphere. Huge reservoirs of fluid, the air. So when you go into the bazaar, the most abundant fluid are water and air. And so end up happening is when you go to the bazaar, in this bazaar, the two important fluids that are being sold are something called Newtonian fluids. Okay, so this is the most commonly available fluid that you have. And the Newtonian fluid has some very simple traits that are going to be very helpful, and we are going to, when we buy Newtonian fluids, we'll also buy the proper constitutive rule for that. We'll see that in the next class. Okay, so in the next class, I'm just going to introduce you to the constitutive rules for the various Newtonian fluids that we are going to be dealing with. Okay, so this time I'll just stop recording right now. Okay, bye.